Okay, these next couple examples, we're going to be factoring completely. And so what that means is that we're probably going to be able to find a GCF, and then there's going to be more factoring that is going to be possible. So if we look at this first example right here, we've got 4x squared minus 4x minus 24. And so what you'll notice is they all have a common factor of 4. So that's what I'm going to start with. I'm going to factor out that 4, and that's going to leave me with x squared minus 1x and then minus 6. And what you'll notice is this trinomial here is factorable. So let's see, what multiplies to give me negative 6 but would add to give me that negative 1 in the middle? Well, that should factor this into x minus 3 and an x plus 2. So negative 3 times 2 gives me that minus 6. And then if I were to multiply the inner and the outer, that's where that minus 1x is coming from. And so that is my fully factored form on that one. Okay, my next one is pretty similar. So when we look at number 2, I'll notice that they do have a common factor of 3, but they also have a common factor of x. So I'm actually going to pull out a 3x. So that would leave me with x squared here. That would leave me with plus 10x here. And that would leave me with plus 25 here. Okay, well, this looks like a perfect square trinomial, which we went over in the previous video. And if you don't recognize that, that's okay. It will happen naturally either way. And so if you look here, what multiplies to give me 25 and add up to 10, it's going to be 5 and 5. So what happens here is my factors are the same. It's x plus 5 and x plus 5. And then we want to go ahead, if we have any common factors, we can bring them together and condense it into x plus 5 squared. And so if you would have recognized it was a perfect square trinomial, you could have kind of gone directly to that x plus 5 squared. If not, not a big deal. Okay, let's look at number 3 here. So let's see, what do they have in common? They both are divisible by 2 and x. So that's what I'm going to factor out. I'm going to factor out a 2x, and that will leave me with x squared minus 121. Well, this is the other special case we looked at called the difference of two squares. So what's going on here is I'm missing that x value. I basically have 0 x's in the middle. So if you want to, if you want to go by our traditional methods, you could try to figure out what multiplies to give me negative 121 and add to give me 0. But what's going to make your life a lot easier is this formula right here. If you have a squared minus b squared, you can factor that into a plus b and a minus b. So that's going to be the easiest way to approach this. So when I look at this, I can rewrite this. Well, I already have x squared, so the first term's already being squared. And then the second term, 121 is a perfect square. That can be written as 11 squared. So now I have the difference of two squares here. And so you take each base and you do one with addition and one with subtraction. So I still have the 2x, don't want to forget about that. And then I'm going to have an x plus 11, and I'm going to have an x minus 11. And so that is the fully factored form of number 3. Okay, I have one left here for us. And so the leading term is negative, so I definitely want to factor out a negative. And then let's see, they're both divisible by 2, so I'm going to factor out a negative 2. And so when I do that, that's going to leave me with positive x to the power of 4, and then that plus 32 is going to be a minus 16. Now, what's left looks kind of unique, something that we probably haven't seen quite yet, but it actually is going to fall into the category of the difference of two squares. So I can manipulate this into each of these being a square right here. Okay, so what I'm going to do here is I can rewrite x to the power 4 as, so I'm trying to figure out what squared would give me that. Well, it would be x squared, so x squared squared. Because if you remember the power rule, power to a power, you would multiply those. And so that's equivalent to x to the power of 4. Then with the 16, I can go ahead and write that as 4 to the power of 2. And so now I have the difference of two squares again. And so the first base is x squared, and the second base is a 4. So now what I'm going to have here is negative 2 times x squared plus 4, and then an x squared minus 4. Looks pretty good, but I actually have a difference of 2 squares again. So if you look right here, x squared minus 4. Now the x squared plus 4, that's going to be stuck because that's the addition of 2 squares. But I do have the difference of 2 squares again right here. So let me go ahead and write that out so we can see what that looks like. So this, once again, I have x squared, so that's already a square. Then that 4 can be written as 2 squared. And so see, now I have the difference of 2 squares again, and so I can break that into 2 binomials. So I still have all this other stuff I need to bring along. And then now this will factor into an x plus 2 and an x minus 2. And that is my answer. And so my suggestion is if you are struggling with any type of factoring, the best thing for you to do would be to multiply all this stuff back together and see that, yes, this is equivalent to what we started with. If you were to FOIL this, you would, let's see, you would get the x squared, and then you'd get a minus 2x, then you'd get a plus 2x, and then you'd get a minus 4. And so you would see that the minus 2 and plus 2 cancel out, and that would take you right back to where we were right here, right? And then if you wanted to, you could go ahead and FOIL this together, and you would see that that would lead us right back up to the red part. And then if you were to distribute the negative 2, you'd be right back to where we started. So I always tell my students, if they're struggling with factoring, go ahead when you get your answer and multiply it back together and just try to see it in both directions, factoring and multiplying it back together. And that goes for any factoring. All right, that's it.